Hi everyone, I'm Ethan, and this is my final presentation for Descriptive Astronomy, where today I'm going to be talking about the global perspective. Now, before we even begin, some of you might be wondering right off the bat, just what is the global perspective in astronomy? To make a long story short, the global perspective is essentially the study and understanding of the solar system and our universe from an Earth-centered point of view. Conversation surrounding this topic usually involves discussing the celestial phenomena that are at play on our planet and also considering Earth's place in the universe. Discussions around this topic typically involve discussing Earth's internal structure, its magnetic field, and its connection with celestial objects in the universe such as the moon and the sun. But to make a short story long, and since this is my final presentation after all, I'm going to be going into detail and talking about these specific celestial phenomena, why they matter to us, and how exactly we went about discovering them. But in order to begin this discussion, we first must take a deep look inside ourselves. And not like this. And no, not like this either. I'm talking about an introspective look inside ourselves like this. This useful diagram shows us the four distinct layers that make up Earth's internal composition: the crust, mantle, outer core, and inner core. We begin our discussion by talking about Earth's outermost layer, thinnest layer, and also the one that we know the most about, the crust. This layer of Earth can also be further divided into two subcategories: continental crust and oceanic crust. Oceanic crust makes up 55% of the Earth's surface and is also primarily submerged beneath the water. Oceanic crust typically tends to be about 3 to 6 miles thick and is usually composed of a material called basalt, a volcanic rock. Continental crust makes up the remaining 45% of Earth's surface, with most of it being above water. Continental crust tends to be much thicker than oceanic crust, ranging between 15 to 45 miles thick. This type of crust is also typically composed of granite, a class of silicate rocks. After making our way past about 5 to 45 miles of Earth's crust, we start to encounter the next level of Earth's composition, and also its largest, the mantle. This layer of Earth is approximately 1,800 miles thick and is composed of silicate rocks that can be both solid and molten. Due to the immense amount of heat and pressure found in this layer of Earth, material found from the mantle typically tends to flow easily and is also very ductile. Occasionally, upper mantle material is ejected during volcanic eruptions. These eruptions are extremely helpful because scientists that examine the material that has been ejected are able to gain a better understanding of the chemical composition of this layer of the Earth. After about 1,800 miles of the crust and the mantle, we start to experience one of the first two layers that makes up Earth's core. The outer core is approximately 1,400 miles thick and is composed primarily of liquid metals such as nickel and iron due to the intense amount of heat. Now, despite the inner core and outer core being composed of identical material, there is a distinction between the two layers due to the state of matter that these metals are found in. Despite having a radius of only about 750 miles, the metals found in Earth's inner core are in a solid state of matter due to the intense amount of pressure. Combined together, the outer core and the inner core have a radius of about 2,160 miles, making it larger than some celestial objects in our solar system such as Mercury, the Moon, and even Mars. Now, due to the factors that I've mentioned, such as the intense amount of heat, pressure, and also the grand size of these layers, you may be wondering, just how exactly did we know what the internal structure of the Earth looks like? After all, if we were attempting to dig a hole right to the center of the Earth in order to further examine it, there would be an intense amount of mechanical and ethical concerns. In fact, humanity's greatest attempt at accomplishing the feat came back in Russia in 1992 at the Kola Superdeep borehole. Now, despite making it over 7.5 miles below the Earth's surface, the Kola Superdeep borehole project was ultimately abandoned due to the consistency of rock at this level and how it is near impossible to drill through. Luckily for us, Earth's internal structure had already been mapped out long before the Kola Superdeep borehole project began, thanks to data recorded from seismological records. Back in 1909, Earth's mantle was first discovered by Croatian seismologist Andrija Mohorovičić. Mohorovičić studied seismic wave data from an earthquake in the Kolpa Valley between Slovenia and Croatia and noticed a difference in the speed at which these waves traveled the deeper they went. Mohorovičić's observations indicated a change in Earth's composition and physical properties, leading to the discovery of what is now known as the mantle. For much of the 1910s and 1920s, the layers past the mantle were thought to just be a purely liquid core until Danish seismologist Inge Lehmann made some groundbreaking discoveries in 1936. Lehmann analyzed P-type waves from seismic wave data and realized that the way these waves reflected indicated a solid inner core surrounded by a liquid outer core. Later advancements in seismological technology helped astronomers confirm these findings and helped us get an idea of what Earth's internal structure really looks like. At this point, you may be wondering, just why exactly does this internal structure matter to us? Well, the internal structure of Earth and its different layers end up playing a key part in maintaining Earth's magnetic field. Our planet's magnetic field is generated thanks to the liquid metal that is moving in the Earth's outer core. As the metal in Earth's outer core goes around, it generates a circulating electrical current with it. And considering the size of our planet and the amount of metal we have inside of our planet, this generates an extremely large magnetic field that extends about 40,000 miles outward towards the direction of the sun. Well, why exactly is this important to us? Well, Earth's magnetic field essentially acts as a shield from the sun's solar wind. Without the help of the magnetic field, the charged particles from the solar wind would be strong enough to erode away our atmosphere, which would in turn turn us into a planet similar to that of Mars. Life on this planet is crazy as we know it, but it's worth it to take a step back and realize why exactly we are here and the factors that contribute to that. So, that's going to be it for my presentation. I hope you enjoyed, and I hope you learned something new. Thank you.